Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook. I'm joined with Greg Volk and Dennis Allen. This is, just kind of a follow-up video from the others. We're going to discuss the Riemann Hypothesis and a couple big announcements. They're big from our end, but I don't know, if they're like groundbreaking, newsworthy, but maybe one of them. All right, so this is just kind of going to be, we're going to go over the proof with a couple discussions on a few issues. It's been 3 years and 3 months. September, we uploaded the paper. I think a year before that, I first sent it to Greg, and then shortly after to Dennis. Some of the findings, and I think, when did we upload the first video? Or do you remember when that was? I could look. It just says 3 years ago, but I don't remember the month.
You did some videos by yourself, 3 years ago, but then we did a couple together about 3 months ago.
Yeah, those were much more recent. And that's what I'm glad you guys are here doing it. So what we're trying to do here is, those were just kind of videos of discussing different matters. This is going to be a presentation of the proof, and with a particular reason in mind. We'll get to that in a second. Since this has been on YouTube, there's been a large number of, not large, but a growing number of Riemann Hypothesis proofs appearing on YouTube. And so every now and then Greg will say, hey, did you see this guy's proof or something? And I go look into it. So kind of, we're going to address one of them. But for example, there's this video out there. This guy, he claims to have proven the Riemann hypothesis and is giving a $10,000 reward if you find a numerical counterexample. There's a number of people who found errors in the proof, but they weren't able to find a numerical counterexample. So I did, and I put it in the comments, and actually the replies became quite numerous. Do you think he paid, Denny? Do you think he paid me? No, he did not pay. Even Greg chimed in on the chat, said pay up.
I remember that.
Yeah, but the issue, and I really believed he was going to pay, but he did that. What came up in the comments, right below the comments, was a gentleman named Artem. Anyone know? He's Ukrainian. Is that how you say his name? I communicate.
Sounds right. I don't know how else you could pronounce it. Artem.
I don't have his accent.
On the second syllable.
So I was too busy looking above and below that. Here we were talking about the $10,000. I was like really convinced that I did not believe for a minute I would get paid. Anyway, yes. So, but then in going through ResearchGate, I came across him, and he had said, "Oh, did you see my proof of the Riemann hypothesis?" And I said, "No." So I went and looked into it. And he said that somebody there found an error in it, and he wanted me to check the error. And I went and found and said, yes, I see there's a major contradiction there. And so I went and discussed it with him. And he said, well, where does it come from? And I backed up. I said, this step here, it seems to be where you did this linear substitution of 1/2. And all of a sudden, that's when things stopped making sense somewhere along that line. So that you want to go reevaluate to see if that was justifiable, and he insisted that it was. No big deal, but after he was going into that, he came to the belief that the Riemann hypothesis must be false. So Artem, this video is for you. I did see you wrote me this morning, so I'm going to reply to the email in a little bit and let you know that we're making a video dedicated to you. So he is a good mathematician. And I like
just to be clear, Jeff,
yes.
He's not the guy who made the video. He's one of the guys who commented on the video.
He is the one. Yeah, the $10,000 different videos. Okay. So there's a number of Riemann hypothesis proofs that popped up in the past year or two. So it's getting messy out there, which is something I want to discuss. It's getting really messy, and a lot of proofs popping up in YouTube. So I don't know if it's a bad trend we've set or what. But since then, I'm seeing a number of Riemann hypothesis videos pop up on YouTube. He has one of them. But if you look here where I've highlighted, he did write possibly the proof of the Riemann hypothesis. So his approach is a lot more professional and educated than the other, which was, we're absolutely certain we're going to offer you money if you find an error. Okay, I like this better. But when he came across that contradiction, he then came convinced that the contradiction meant that the Riemann hypothesis was wrong. So that's when I said, okay, I'm making a video for him because he needs to understand this because he has read our proof. And so the questions that he raised, we'll get to them, are probably questions that other people may have. Although if it's in your mind that you are going to solve the Riemann hypothesis first, then you want to find errors in other people's. But it's not. He didn't find any error. But we're going to discuss that. So this video is really for him. But let's just kind of say, Sunday, he even uploaded his latest work, which is what he wants me to look over. And I honestly, I don't know that I'm going to. I'll talk with him about that later. But here it is. He has this generalized universality theorem. And so he used it to prove the Riemann hypothesis, and then he used it to disprove it. But I like it. It's very advanced in a lot of ways. All right, so this video is for him and for other people. How do we really know that the Riemann hypothesis is correct? All right. Well, you can go look at our proof. And we're going to go over the proof, and we're going to dumb it down. This is something that if you're walking the street, you could be able to explain this proof to anyone in the street, as long as they know the Riemann hypothesis already. So it's not a complicated proof.
Can I just jump in real quick and say, well, first of all, to note that this is ResearchGate's got over 12,000 reads on this paper. However, the original paper that was published on September 2020 was longer, and we put a shorter version in. And this is now. Did you actually replace the longer version with the shorter version? Okay.
Yes. So
most people read the longer version. That's what I'm trying to get at.
So that's the other issue, is we're trying to simplify and get to the heart of the matter so that no one's distracted by the research, that which is involved, any background on oscillators. None of that's necessary for the proof. So that is still at ResearchGate, moved into a different location. You can go see that from my profile. And the paper, the final version that we are presenting, is the shortened version, just so people can get to the proof, get through it, and that is up here. Yes, there have been a number of drafts, and the core.
That's putting it mildly.
Yeah, the core issue has not changed. The equation's been there from the beginning, and the final result of that that any non-trivial zeros off the critical line are mathematically impossible because they cannot be symmetrical off the critical line. That has not changed. But kind of, so we've gone through it. But this is essentially everything that was in there except for some of the notation and so on and so forth. Yeah. All right, so let's go. This is the theorem. Maybe Greg, you could read this. That would be great. This is the theorem in the paper. This is what we're going to prove.
Okay, theorem. Let let rho be a non-trivial zero of the Riemann zeta function, rho of h, a hypothetical non-trivial zero off the critical line. And is that my screen doesn't go all the way over?
No, it says
okay. Because there are only two. Because there was covered up. Because there are only two types of zeros of the Riemann zeta function, and they are mutually exclusive, such that the first type contains all the critical zeros. Riemann of rho equals a half, and the second type does not comply with. I'm sorry. What's that symbol?
Imaginary part.
Imaginary part of rho of h equals the imaginary part of 1 minus rho of h bar, or the real part of rho of h plus the real part of 1 minus rho of h. Shouldn't that be of h? Oh, rho to the h. Okay,
there's a couple typos in there. The h is up to the superscript rather than the subscript. That's just in this PowerPoint presentation.
Yeah, all those, they should all be subscripts. Right?
Yeah, they are, but you'll see some of that in this, because I clicked through this PowerPoint.
Okay, I'm in the middle of a sentence here, comma, the Riemann hypothesis, if all that's true, then the Riemann hypothesis would be correct. All non-trivial zeros of the Riemann zeta function have a real part 1/2. So in other words, only the first part is true.
All right, so Denny, you thought that this would be the approach we take. Can you explain that last equation, the imaginary parts and the real parts summing to 1 in the critical strip?
Well, they're equally they're mirrored in the critical line.
Correct.
So the 1 minus rho sub h, and that's to the right of the critical line 1/2, and wait a minute.
That's right. Yeah, and they sum to what?
They would have to sum to 1, yeah.
Yeah, so does 1/3 plus 2/3 equal 1? Yeah,
Yeah.
yeah, and 1/4 and 3/4. So and then 1/2 plus 1/2 equals 1. So anything in that area, yeah, it's going to have that. And with the symmetric vertices property, which we'll kind of discuss a little bit, the imaginary parts of Greg, you can explain the row bar. That means complex conjugates, just for anyone says. So
Yeah.
the imaginary parts of these are going to be equal. That means they're going to be horizontal, on the plane. So we'll kind of get into that. But basically, that's all we're saying. The imaginary parts of these two zeros are going to be equal, and the sum of the real parts is going to equal 1. That is required. And it's from the zeta function. It doesn't have anything to do with the functional equation. It doesn't have anything to do with any of the unique forms. It has to do with the zeta function itself. So this is an issue, so we should get them. So the functional equation is kind of taboo in journals. If a Riemann hypothesis proof comes to the editors, and I've read this from them, and if any paper starts with this functional equation at the beginning, they immediately throw it to the slush pile. And the reason is because it has never yielded any information other than perhaps that trivial zeros exist. So it's never really, it was good for what Riemann was doing, but it's not very useful in the hypothesis.
Proving it, yeah.
Yeah. So, but what is interesting is that the symmetric vertices property does not follow from the form of the functional equation. In fact, if you read his paper, Riemann used the symmetric vertices property to put the functional equation together. So if the functional equation came after the finding, Greg, would we say that is after?
Cause and effect. Yeah.
Or is it before?
Yeah,
So
yeah.
there are still mathematicians, and I don't want to mention names because I still want their feedback, but some that I very much respect, but I'm losing that. I'm being honest with you. I'm starting to lose it because I got one response saying, I haven't found any errors in the paper, but you relied too much on the functional equation. And my response is, we don't use the functional equation at all. It's not in the proof at all. So the symmetric vertices property is a function is a phenomenon of the zeta function itself. So I'm going to do some shapes. Greg loves shapes, so I'm going to get him involved here. So,
Okay.
All right. So we're going to do group theory and set theory. Oh, let me go back really quick to mutually exclusive. Greg, could you tell me what mutually exclusive means?
Well, it's either one or the other are true. They can't both be true. That's
Yeah.
mutually exclusive.
And if they're in sets, if it's in one set, can it be in another set?
Nope.
If all the zeros, you see I have this zeta equals 0. If all the zeros are a zeta function set to 0, does that include all the zeros? Maybe
Well, you're making these tough
maybe all
questions,
could
Jeff.
involve some. If half
No,
the tree, if
and it
half
wouldn't
the
be
apples
all.
if half the apples are on the tree and half are on the ground, are they all on the ground?
No.
No. Okay. So that's mutually exclusive, right? All right. So
Yeah.
let's just say that let's use shapes and let's represent this oval as being containing all the zeros of the zeta function. Does that make sense?
Mm-hmm.
All right, good. Let me know if any of this does not make sense. So if you have two different functions or two different forms of the function, when you use the word form, you mean shape, right? So the shape or the form of the function is going to be different. So if I take Play-Doh and I take like a triangle, a pyramid, and I cover it up with clay, all right? Then I can say that triangle or that pyramid fits inside the clay, and I can change the outside form of it, but I couldn't hide, like, let's say, a triangle in an oval if they have the same width of the base, because it'd be popping out. Okay, so I want to show this with form and how form doesn't change anything. So we have these different shapes of zeros. They have slightly different properties. Now let's look at the triangle first. Draw a line. Do you guys see my cursor, by the way? I don't know if you guys
Yep.
see. Good. All right, so draw a line right down the middle and split that triangle in half. And then the star, split it right in half with the vertical line, and the hexagon and the circle. Okay? Which one of these shapes, if I split right down the middle, do not have symmetric vertices?
Well, depending, they all have symmetries of one kind. I mean,
What's that?
some have, the circle has more symmetries than the
Does it have
triangle,
vertices
but
though?
no, I guess
Okay,
there's an
so it doesn't
infinite
have
number.
any
You could say
vertices.
there's either zero or an infinite number, depending on how
Yeah,
you define
exactly.
it.
All right. So I would say, I think by definition, a circle doesn't have any points or cusps or anything, right? So, all right. So this would be the one that doesn't have symmetry across the critical line. We'll make that vertical line be the critical line in our mind, just so we understand shape. Okay. So we're going to call that the trivial zeros. We're going to represent that shape as the trivial zeros. All right. All the zeros must fit into the definition that they're zero, right? Because this purple oval fits all the zeros. So they all must fit into this square. And all of these shapes do fit into the squares. They all have a property that the zeta function is zero. Many different types of zeros. Okay. So that circle we're going to put into a different group. We're going to call them trivial zeros. Does that make sense? We now have two groups. Trivial zeros over here in the green oval. And in the orange, we have those that are hypothetical. They may have 1/2, they may not, but they are symmetric across that critical line. Does that make sense? Am I getting confused in the issue, Greg or Denny?
Well, I just want to first of all clarify that this is the first time either Denny or I have seen this. I'm still misunderstanding.
I put it in a different
Okay, so
video.
you're saying the circle is different because there are no points to define it.
Well, we're just going to talk about mutual exclusivity, and we're going to kind of draw an
Because I
analogy.
mean, there is a symmetry, but maybe not the
Yeah,
kind
there
you're
is a
talking
symmetry,
about.
but we're talking about symmetric vertices.
Okay.
So, all right.
All right.
Not an exact analogy, but just kind of like we're just talking about form
Okay,
and shape.
okay.
Because what I really want people to get out of this is this functional equation is irrelevant for our paper because it's just we're using a different form. All right, so we'll watch what we do. This is what essentially happens. With the functional equation, we have gotten, or at least by people studying it, trivial zeros and non-trivial zeros. That's the two groups, right? Well, we're going to change that in this proof. So what we're going to do is we're going to add, we're going to use a different form, and just like the clay and the triangle, they're no longer going to fit into this definition over here because we're going to change it. The new form is this oscillator equation, which is up here in the upper left-hand corner. All right, so now it has a little different shape, and we can't see certain things that we thought might exist. We thought there might be hypothetical zeros off the critical line with the functional equation, but with this form, we're going to show that they can't exist.
Can I just interject
Please.
one more time? The A sub s, B sub s, and C sub s in the equation you're defining are not yet determined. So we could say that about any function at this point.
Exactly. Just talk about the form.
We're just saying we're going to choose to put it in this form.
Yes.
Because we're going to discover some things when we do that. But at this point, any function could have that form.
Exactly. We're going to regroup them according to the form of the function itself. And here's how we do it. All right, we set this to equal to 0. So if this is equal to the zeta function, Greg, and it equals 0, does this mean some of the zeros are in there?
Well, you're asking some tough ones here.
You'd be surprised. There's some people think there's gray area in this.
Okay, all right.
If it's 0, then it means all the
If
zeros.
A equals B and B equals C, then A equals C. That's what you're asking.
So
and yeah, I'd say so.
All right, so there's none hiding. Like maybe the non-trivial zeros are hiding over in this corner.
No, they're not.
It can't. They're all included. Okay, so if this is the form here, n equals 0, and we solve for upsilon here in this, we get the zeros in terms of this, in terms of upsilon as this. Okay, so this is where it gets quite useful for us. The shape changes. This now will be shown is a geometric series or something like that. All right. Because of that, we get two different types of zeros. We have those where zeta function equals 0 and upsilon equals 0, and that happens only when the real part of s equals 1/2. The other type is when zeta function equals 0 and upsilon function does not equal 0, and the Riemann or the real part of s does not equal 1/2. They're mutually exclusive. The real part of 1/2 must be over in this group and not in the other. So these guys got to kind of change places since they're non-trivial zeros, but some of them don't have real part 1/2. They have to get out of this new grouping. And so they don't fit. That star does not fit into the triangle. The hexagon does not fit in the triangle. So we have to move them. Do they fit into this definition? Yes, they do. So we now moved them out, and we get rid of the functional equation entirely. Does that make sense?
Jeff, wait, not quite.
Good. Yeah.
I'm still trying to understand the significance of the various colors. There's the green and the
There's no
sort of light orange.
There's no significance in that.
Okay, but the two equations that you have on the bottom, you have Riemann sub s equals a half, Riemann sub s doesn't equal a half. Those are mutually exclusive, are they not? So
Yes.
there should be two regions and not three. I'm seeing three regions, including the purple. So that's where I'm confused. But maybe that's not
That's
what those
just
represent.
the space of all the zeros. I just kind of
Okay, but
I
the purple
divided-
doesn't exist because those two are mutually exclusive.
Right. I should have put like take an oval and divide it in half and had one half as one group.
Okay.
But
All
anyway,
right. And I was trying to figure out how the
you're right.
square
That is
fit
a
into the
terrible
whole thing. 'Cause
representation. I'm going to do this. All right. Let's shut off the video and start all over. No.
I'm sorry.
No, you're right. I like that because you helped clarifying it. Okay. So, but basically, what I'm saying is we're kind of redefining the groups. We're no longer talking trivial and non-trivial. We're talking about real part equals 1/2 or real part not equal 1/2.
Okay.
When that happens, upsilon goes to 0 by the form of this function. Okay? And so then at the end of the proof, what we're going to do is show that, look, these don't fit into this group either. We have to eliminate those non-trivial zeros and those non-trivial zeros because this circle over here is the group that has no symmetric vertices. So they don't fit there. They have symmetric vertices. So they don't fit in anywhere. Therefore, they don't exist.
And the ones that you're using to represent the circles, those are the trivial zeros?
Yeah. So what we're left
and that's all that's left.
at the end of the proof,
now I
all
see
we
where you're
get is
going.
the trivial zeros and the non-trivial zeros.
Gotcha.
And the non-trivial zeros all have real part 1/2. The ones that didn't have 1/2 are eliminated pretty early on. All right, because we grouped them out. They don't have 1/2 real part 1/2, so they're out. They're in a different group. This group cannot be in here, and this group cannot be in here. But those other groups, by doing that, we see that they don't fit over here either. They're not possible, mathematically possible. So we're going to go now look at the equations instead of this abstract, thing. But I think there's some people, maybe non-mathematicians, who will like to look at shapes a lot better than what we're going to show. Even though it's very simple. So let's keep it really simple. And I like this. I think you guys probably hate it by now, but it really kind of starts very simple. We can look at the two types that we have here, these two groupings. All right, right here, these two.
I know where you're going.
Yeah. So we have this. We can look at it in this very, very simple elementary equation: a plus b plus c equals 0. We can say the two types of zeros that fit in this. The first type is going to be the type with the real part 1/2. But let's just look at it. Is when one of the terms equals 0. None of the other terms can equal 0, but one of the terms equals 0, and the other two terms negate each other. Does that make sense? Okay, so one term it goes to 0, the other two terms negate each other. That's a linear solution. If you take them and plot that, they're going to kind of all fall in a line. Type 2 is a little different because we have a couple different scenarios that could arise. We could have a plus c equals minus b. This is where none of them are 0. None of the terms equal 0. But the two, well, they might have be 0, but this is the properties that they always have two terms negate the third. Okay? And that, when you have those, I think it was 3 different possibilities. We're going to call that a type 2, and that is, if you graph it, a planar solution. All right, is there type 3s? A lot of people raised this, but we had discussed mutually exclusivity. So that
you could say that if all 3 are 0, but that's really just a special case of type 1. Oh,
yeah, it is. So let's take it. So is there type 3? They're all zeros. And you could say, yes, well, the a does equal minus b because minus 1 times 0 is going to equal 0. But it's also a type 2 because the other definition is true as well. That would say they're not mutually exclusive because the type 3 is in both. So,
well, you could also say that type 2 is in general a special, or a type 1 is a special case of type 2 because in this case b equals 0. You're back at type 1. But anyway.
Yeah. So the cool thing is we can look at this, but we have in our proof is type 3 is not possible either way.
Yep.
Okay, so here, how do we do this? All right, so if we want a plus b plus c equals the zeta function, that's the goal, is to get it into that form. What's a good way to start? I like the harmonic oscillator. Greg, can you tell us a little bit about what is a harmonic oscillator for the lay people?
I just wanted to point out that with the three terms, just to put closure to that idea, it's possible to have 1 0 or all zeros, but it's not. And it's possible to have no zeros, but it is not possible to have 2 zeros. You can't have A not 0 and B and C both being zeros, because then if you want the result to be 0. So just
right. Oh, that's good. That's good. Yes, in case somebody would come up with
that. Getting now to your question, the harmonic oscillator is basically three terms. So we have A, B, and C. That's where the three terms come from. And we're choosing to put it into a form that's going to look like that. And we want to have, obviously, the three terms be composed of derivatives or kinds of derivatives. So the omega represents, I guess, the frequencies, kind of they're increasing with each of the terms, and then the derivative of C sub s is decreasing with each of the terms. So the two together are omega's kind of like inverse of time. So we're either going to get an omega term or we're going to get a derivative of time. And so the unit wise, I guess they're all going to be equal to some number. So that's the way an electrical engineer would look at an equation like that.
And you studied this in college.
Well, yeah, we would see the mu sub s term as sort of like the damping term. That's what I think of it. The term to the second power would be that. If it were 0, then there'd be no damping. It would
you
be
mean the
regular oscillator. Upsilon. I'm sorry.
Yeah, upsilon would be analogous to what?
0. I don't know my Greek symbols as well as I should.
That's okay.
When that is 0, then we have a true harmonic oscillator that never vanishes. Whereas with the upsilon of s being non-zero, then it's going to dampen. It's going to eventually.
Yeah, so they call that
it's going to be like a sine wave that just gets smaller and smaller and smaller. So that's how.
And with an example with the derivatives, can you give me an example? Like if you have, let's say, distance or position is C of S's position. What would be the derivative?
It's very common in electrical circuits for equations like this to show up, because a capacitor is a lagging time, and inductor is leading time, and so then the resistor would be the middle term, the damping term, and we can get an RLC type circuit worked out with that. Maybe that's thinking of it in terms of distance and time. I mean, you can think of I don't know. You can think of a block on a harmonic oscillator, and then the resistance would be how much the K term, how much it's dragging each time. Eventually it would come to a halt and stop oscillating.
Yeah. All right.
Does
So
that answer?
Yeah. No. So in one sentence, what is an oscillator?
It's just a two-dimensional, a degree 2 differential equation.
Okay. All right, good. So, and then if we would take t at 0, what would you say? That's the beginning or the end of the oscillations?
Well, that would be what I would think of as an initial condition. So we'd say, generally speaking, if I have a degree 2 differential equations, then I need to have I need to know where it is at a certain point in time. It doesn't have to be 0, but some point in time. And I also need to know how fast it's moving at that point in time. So I would need 2 initial conditions to be able to satisfy an oscillator of degree 2.
Good. Good. Okay. So now if we take this is the lemma here, and we have this C of S of t, and if we take the derivatives of this, we get the 1 over s minus 1, and then
derivative
minus
with respect to t, right?
Correct.
Yeah, with respect to s.
Correct. All right, good. And so this just kind of showing what this is. So we have everything defined, and upsilon follows this definition. Why does it be good? Let's say, Denny, why might it be good to define something in terms of an infinite series or an integral? Is there a reason mathematicians do this?
Well, integrals are uncertain. You don't always know how to get integral in closed form. On the other hand, if it's a series, you don't know where, how long, what the circle of convergence is in the complex plane.
Well, if it's uncertain, why would people use it as definition? Let's go to the next slide, and I want to see. Well, here, we'll come back to that. All right, so I kind of going with somewhere with that. All right, so let's first look here to some little issue that Artem has brought up, and it's something that Denny, you and I kind of discussed in the beginning. You brought up and you said to be very careful with it, and we all were very careful. I'm looking for my glasses. Hold on.
I'm not careful.
All right.
I throw caution to the wind.
Yeah. So is this function upsilon analytic? Just by looking at it, is upsilon analytic?
Well, the integral would be the problem here.
Are you sure?
Oh no, wait, that's an S bar. Isn't it?
Yeah, S bar. Very good. Mm-hmm.
Well, yeah, there could be a problem with that term being non-analytic.
Right.
W equals Z bar. It's not analytic.
That's right. So we're gonna issue with that. So we gotta be very careful with that, and not use analysis when dealing with that complex conjugate. But we can use algebra, right, with a non-analytic function.
Yeah.
Yeah, we can use algebra, and we'll get to that, and you can explain maybe more. All right, so at t equals 0, are we saying that the zeta function is not analytic because it's equal to this? So if we have upsilon in there, upsilon's not analytic. We have that as a term. Are we saying that the zeta function of s is not analytic when it's already been defined to be known to be analytic? The answer is this: no. If it can't, all the non-analytic properties, the complex conjugates, cancel out at t equals 0, then we are left with an analytic function. If you take an analytic function, Denny, and you multiply it by a non-analytic function, it becomes non-analytic, right? But if we divide that right back out, it becomes analytic again. Is it that simple?
Yeah.
Yeah, it's that simple. All right, good. A lot of people may not understand that, and so let's kind of see if this does cancel in this way. So we'll begin with the decay rate. Greg, I don't mean to put you on a spot. Do you remember how the decay rate relates to the damping ratio in an oscillator?
Yeah, I mean the decay rate is, if you solve a differential equation, you're going to get a decay that is basically the upsilon coefficient, the coefficient of the middle term. It's going to be e to the that times some other stuff.
All right, good.
That's going to be your decay rate.
So they're intricately
E to the
linked.
minus that. Anyway.
So in this, we define here the decay rate as this. Now remember that we're not describing a real oscillator, just what do you call it? Mathematical analogy. It's mathematically equivalent, but we're not describing a real world oscillator.
Yeah, because you can have complex numbers.
Yeah, there are.
Oscillator equations I ever studied had real numbers.
That's right.
That's
Yeah.
not true. If you ever study circuit theory, they do use impedance rather than resistance.
All the time, yeah.
Yeah. There are some complex, I've read some papers when I was kind of doing this years ago. There are some people that go into complex angles and some really interesting concepts, which I think
that's very common in electrical engineering to talk about. We go back from a complex number a plus ib, and then that is related to some the a squared plus b squared square root. That would be the magnitude, and that would be at an angle, which would be related to the arctangent of the b over a.
Yeah, so it very well could represent something real in nature.
We go back and forth all the time.
Yeah,
for various reasons.
Good. All right, but this function here, you see there are no complex conjugates, no absolute values, nothing. So these are all real and natural arguments in here, and so we're fine with this analytic. So what we're going to do is analytically continue this function using the Abel-Plana formula. Okay, and this is what you get. It actually kind of it's very straightforward applying this to the Abel-Plana formula. Some functions don't like to be converted exactly, and you might get something divided by 0, and you have to come to the solution. But this one happens to work very nicely, so that helps us. And this
Can
is
I
that.
just interject one more time, just
Yeah.
for those. I don't know if anybody who's gotten this far is not a math guy. Probably they all are.
Mm-hmm.
But Abel-Plana is a form that was discovered. Actually, it was discovered more generally, but it was applied to zeta sub s way back in the before zeta sub s even existed. What, about 1820 or something like that?
It was 50 years before Riemann's paper was written.
Right, exactly. So that's what that was, and it was applied. When you're saying the Abel-Plana formula, you're thinking of the Abel-Plana applied to just the Riemann hypothesis.
Yeah, well, this function right here, we're applying this infinite series to the Abel-Plana formula. So you could take any infinite series. Some work out better than others. This one happens to work out nicely. And we're going to take this infinite series and apply it to Abel-Plana formula. It's a way of analytically continuing some infinite series to the entire complex plane. This one works very nicely. And remember what Greg was talking about is the relationship between the damping ratio and the decay rate and the frequency. And this is how they're related. It's just simple product, right? So this is the decay rate is equal to the frequency. What is the fundamental frequency, Greg? Can you explain that really quick? Fundamental frequency of an oscillator.
Well, I mean, you could think of the again, getting back to like the block. It's a spring attached to a block. It's how fast does it go back and forth. That doesn't change, even though it damps and it goes a smaller each time. It doesn't go faster as it gets smaller. It's still the same frequency, and that would be omega. It's related to how if you, in this case, it'd be the mass times the related to the spring constant. I think it's K over M or something like that. And so it's telling you something about the system overall. So it's in the case of what was the other electrical circuits, it's going to be it's going to be related to the LC. I think it's the product of L, the inductor, times the C, the capacitor, 1 over the square root of that.
That's good memory. Better than mine. So that's what we're doing here is we're just kind of constructing, we're going to construct upsilon beginning with the decay rate, and we're going to multiply it by this fundamental frequency. We're going to build the oscillator. Okay. So next we're going to substitute in I times complex conjugate of S in for the fundamental frequency. All right. And now we have this. We're no longer calling it.
Can I interrupt one more time? I'm sorry to
Yeah.
keep interrupting. I just wanted to just add one more point to that, and that is that omega is a function of the entire system. It's not a function of any one individual component.
Good. Yes. Okay. Good. That is
So
important.
that may come into play when you're explaining later.
Yes, it is. Yeah, it's very important. Okay. So yeah, fundamental. It's kind of, I think, way I think of it is at its without any external forces. This is the frequency the system would have.
Right.
I think that's the way I look at it.
That's
Okay.
right.
All right. So now we have substituted Q. I forgot to mention that. We're going to substitute the complex conjugate of S in everywhere for Q. So we're putting all of these non-analytic properties in there and just kind of taking it to where we want to go. And then if we multiply A of S times omega, or no, I'm sorry. We're going to divide A of S divided by omega. We get upsilon, because you remember that little ratio, that little product. So there we have upsilon, and we're going to call this upsilon. We define this now, what we just did with the analytic continuation of this series, make a couple substitutions, and we're going to just divide it and substitute.
Can
Denny,
I
are
interrupt
there
one
any...
more time? Well, I'm sorry.
Yeah.
I just want to clarify. No, go back to the page you were just at.
Sorry.
The difference between omega naught and omega s. Omega naught can be thought of as sort of the natural frequency, whereas omega s can be thought of as, if we think of the zeta sub s being like a forcing function, it's trying to get this thing going. Omega s is related to that frequency. So there's two different frequencies: the natural frequency of the system and a frequency of the forcing function. If you want to think.
Yeah, we could also think of it like, suppose we have this big contraption that built an oscillator in the room, and we have many different size strings that's going to change the thing. We can call that S. So we can substitute any different size string for the oscillator, and that would be our different arguments S. It's kind of the way of thinking of it.
Right.
But
And
the
also
machine
S can be
still works.
complex.
Yeah. And the machine still works the same, but it's going to have different properties based on X. Or S, sorry. So in this way, the fundamental frequency is going to change dependent on S. All right, so moving on. Denny, is there any problem with multiplying and substituting anything in what we just did here in math? I mean, we're defining things. Is there anything odd or tricky we're doing here?
Well, I don't know about tricky. I mean, most of your audience will think it's tricky.
Okay, but all right, in 1 or 2 sentences, did I do anything wrong here? Am I presenting anything that's outlandish
No,
or?
it looks all right to me.
All right, then let's move on. Yeah, no, that's good. That's good. That's all I want. Just want confirmation of that. All right, now since we have all we've done with is multiply this omega, we can also do the same thing with the infinite series, and we have an infinite series representation of upsilon, even though upsilon is not analytic. You see, so we didn't take the infinite series and do the analytic continuation of upsilon because it's not analytic. But alpha was, the decay rate was analytic, and so we just simply multiplied it, and we now have a way so we can have infinite series representation of upsilon and infinite but it's only going to be in a certain region when the real part of S is greater than 1. And we also have this analytic, not analytic, sorry. This function that
Denny
is...
a question before we go on?
Go
I'm
ahead.
sorry to keep interrupting, but Denny, can you give me a definition? Denny's the math guy. I'm the engineering.
No, you're a math guy too. Everyone, we have
a
different...
little bit, but anyway, Denny, could you please give me a definition of analytic? What exactly does that mean?
Yeah, good. A lot of people will need to know that. Mm-hmm.
Well, it has to do with the Cauchy-Riemann equations being satisfied.
Okay, but we don't. Most people listening won't know what those are.
No, well, how else can I explain it? Golly, I'm drawing a blank here. What, Greg? Go ahead.
Put you on the spot. Well, no, I like I said, I'm kind of in a blank right now. Exactly what analytic means. So on how you can recognize something as being analytic
all right.
or not.
You know, you guys both know the
grade
surprise. You guys both know the surprise. Or at the end of the video, right?
Yeah.
So think of the work we've done on that. It involved a lot of limits, right?
Mm-hmm.
So that's kind of, because the function is analytic, we can take those limits. It's nice and smooth. So there's something to do with, you can kind of think of it in terms of topology, which you like. And if you're going to take, let's see, if you have this complex conjugate or an absolute value in there, it's not going to be analytic around that area. So you can't take some nice smooth limit around there. That's some of the limitations of not being analytic. Am I right in saying that, Denny?
Yeah, if you take the limit coming in from all directions in the complex plane, you may have trouble with that conjugate in there because S equals omega as a function of omega. I lost my train of thought.
Well, can I just throw in what I think and I could be wrong about this, but I think the definition of analytic is that Jeff used the word smooth, and that triggered for me. Not only is that there are no breaks in the function, but there's no breaks in the derivative of the function or the derivative of the derivative and so on. Is that what analytic means?
Yeah,
kind of.
If you have a Taylor series, it converges with a non-zero radius.
Okay.
You may have cusp singularities in the function. Like for instance, with the zeta function, it's analytic, but you do have this pole at s equals 1.
Right.
And so it's still considered analytic. Yes. So
so analytic is a little looser than what I just described.
It's just different. But here's the issue. If you're going to do anything and take the limit of a function, let's say now we take upsilon and we're going to take the limit to s equals 1. Most people would say, nope, I'm dropping this paper now. You can't do that. Mm-hmm. So there's certain things you can't do with a function that's not analytic. Now what I can do is I can go apply s equals 0.008 this function and get some output. That I can do. Do it make sense? So it's undefined. It's just not analytic around, certain areas. And now there's an article on Wikipedia involving the absolute value, because there's a way to represent the complex conjugate as, I can't remember what it is, absolute value of s squared or something like that. They kind of, can be expressed. So they both have the same issue. And it does create an issue in a certain region. But doesn't mean that we don't get an output. It's not the same thing as a singularity. So the s equals 1 is a pole in the zeta function, even though the function itself is analytic. So
Jeff, just to be clear, like inverse tangent, that's the one that it goes up like this and up like it keeps doing the same thing, but it's got an infinite number of poles. Like also the gamma function is another one that when you're talking about negative numbers, you got a loop here and another loop there and then a loop there that goes up and down. There's all kinds of poles, but they're both analytic. Is that not right?
Well,
that's Denny.
I'm used to thinking of analytic around a certain point.
Okay.
You have a Laurent series. You have a Laurent series which has no negative exponents. A Taylor series, really.
Right.
All right. Good. We could.
We'll move on.
We'll talk. Yeah, because we've got to. The important thing is if it all cancels out, then we don't need to worry about it. And if we're doing algebraic manipulations, we don't need to worry about it. So we can do algebraic manipulation.
My only concern there is again, when you say it all cancels out, you can only do 0 over 0. In other words, you can only cancel things out when they're not 0. Is what I'm getting at.
We're going to get to that, so we'll talk about it. We'll get there, okay?
Okay.
We're almost there.
Good.
All right. Okay, so we have this infinite series representation. All right, we're going to substitute C into the oscillator. We have our oscillator fully defined. All right, so with everything. And at t equals 0, that's what we get. So the oscillator becomes equivalent to the zeta function. Now,
only at t equals 0.
Yes, at t equals 0. So that is exactly, it reduces, and you see everything around it drops out except for this sum right here. Everything else cancels out. And so you can put this into any calculator to check. And the oscillator, the Riemann oscillator, is equivalent to the zeta function at t equals 0. All right? That means what? It means we can use the form of the Riemann oscillator. We cannot use it for analysis, but we can use it algebraically manipulate it as such. Okay, so the same thing we can do, you'll see the same thing with both forms of upsilon, or both forms of, upsilon, the integral or the infinite series, both cancel out nice and neat, just as we would expect to the zeta function. So, the oscillator reduces to the zeta function at t equals 0. So that's in the paper. Anyone can check it. There's nothing, we didn't do any analysis. We're just saying, look, this is why it is equal to the zeta function. Even though there are non-analytic components in there, all of them cancel out, and we see that the oscillator is exactly equal to zeta of s. Does that make sense? All right, I don't want to say too much, it'll make it more confusing. Any questions?
I don't remember seeing it in that form before, but that's okay.
It's in the paper.
That's the form we got in the paper?
Yeah.
All right. It looks new to me.
Yeah.
All right. The part that's on the outside, I recognize. But okay.
Yeah, this is in there. It's in proof of lemma 1. All right. That's proof of lemma 1. Is all we're doing is we're constructing the Riemann oscillator. Now, everything in the oscillator is defined and in explicit form. Everything is explicit form except for omega and upsilon, but you see what happens to the derivatives. This is what goes on. And you remember the whole a plus b plus c equals 0 we were talking about earlier? We have that now with these terms. So we have one term here, and third term here. Greg, can this first term equal 0? Because that's the second lemma. It's saying that only the second term has zeros. Does the first term have 0?
Well, only if s is infinity.
Well, Denny, could we even say that?
Infinity.
No, because 0 has no reciprocal. So therefore,
Well, yeah,
Then there are no zeros.
either way you look at it, it's the same. Either S is at the point of infinity on the Riemann sphere, or you can say that you can't divide by zero.
Yeah. Well, I mean, S equals 1, but that gives you an infinity, which we know there's a pole at zeta sub S.
okay, look, does zero have a reciprocal?
No.
By definition, it does not. Therefore, we cannot say this goes to zero.
Okay.
This has no roots. Does this term? Yeah, we're not doing limits.
Okay.
Does this term over here have any zeros?
No.
Omega S could be 0 if S is equal 0, but that wouldn't be a 0 of the zeta function, right? So 0, S equals 0 is not a 0 of the zeta function. So that one's never going to go to 0 for any zeros, because that has no reciprocal. We got the center, the middle term. So at this point, we're at B equals 0. Well, why does it go to 0? It wouldn't be because of this factor, because that's the same issue. 0 is no reciprocal, so this won't go to 0. Omega S, we know, can't go to 0 because it's not a 0 of the zeta function. So the only thing that could go to 0 for any of the zeta functions here, if for type 1, or it would be, or for any time, only the second term of the zeta function in the form of our oscillator has zeros when zeta equals 0. Only one possible is here. Do we agree? It's the simplest proof right here. It takes 2 sentences. All right.
Yep.
We're just saying only one of these terms goes 0. Then we can move on to the type 1 and type 2 types of zeros. Now this is the heart of the proof. All right, the mutual exclusivity property, or mutually exclusive property. So this is the lemma. Greg, why don't you read really quick, if you may?
All right. The Riemann zeta function has the mutually exclusive property zeta sub rho equals 0 or
That's the and.
Epsilon of rho, huh?
That's the and symbol.
Oh, and I said or.
That's okay.
Yeah, that's and. I know that. You're embarrassing me. Anyway,
I'm sorry,
that
but I had
equals
to
0,
stop.
which is equivalent to saying that the real part of rho is a half.
Good.
And the zeta sub rho equals 0 and epsilon of 0 does not equal 0 is equivalent to the real part of rho does not equal half. So we're basically saying that whole complicated mess is equivalent to saying the real is a half, and when the whole complicated mess is not 0, then Riemann of 0 is not a half.
Okay, good. So we consider this now 2 groups. We looked at those ovals before. So this is group 1, type 1, and this is type 2. We're going to just define them as that. It's what we're going to prove. This is the lemma. Okay. So, all right, we take this and we set it to 0. Greg, does all the zeros mean some of the zeros?
You're giving me these. I can answer the easy questions.
You can answer
No,
all of them.
means all.
Nobody can answer all the questions when put on the spot. It's hard, I know. Oh, next time you run it, I'll be the one embarrassed. Like, I don't know. I don't. But all typically means all, and maybe there's some context of mathematicians. No, all always means all. Okay, so if we're setting this to 0, then we are including all of the zeros in terms, and we're solving them. This is the solution in terms of upsilon. Right there, in explicit form. It's very simple. I times, the PowerPoint doesn't really do the math display math very good.
You're assuming here that omega sub s is equal to I times.
Well, yeah, we defined it as that. So yes, exactly. Omega sub s is I times the conjugate of s. So this is what it reduces in explicit form for all the zeros.
Yep.
This is what it looks like. Okay, let's move on. All right, so let's just kind of see where we get to the type 1 zeros. Okay, so type 1 zeros is when the B term, the second term, also goes to 0. That means upsilon goes to 0. So here is upsilon. We set it to 0, and then we get that explicit form of the second equality here. And that numerator can be rewritten as I times these 2 factors. The factor on the left has no zeros, okay? Because a real number cannot be equal to a complex number by definition. And 0, since 1 is here, you're never going to be able to subtract that 1 out. This is never going to be equal to...
Wait a minute. A real number can equal a complex number if the imaginary part's 0.
Well, Yeah, a real number
Well, I
is
thought
a
what you just said
complex
didn't.
number.
Not exactly. Go ahead. By that definition, it can become a real number, but it's no longer considered in the same respect and the same time a complex number. So do you understand? So we wouldn't say so complex. Let's see, imaginary number is by definition what? A real number multiplied by I.
Sure.
And a complex number is an imaginary part plus a real part. So if
the way you said it, I think I know what your point is, but you didn't quite say it.
That's probably true. But the long and short of it is, by definition, this factor cannot equal 0. It will never go to 0 because you're never going to be able to negate this this real number. And you put it in any calculator, and it's going to say there's 0 solutions.
I see what you're saying. Okay.
Okay.
Yeah. Because the imaginary part, by definition, is a real number itself.
Yes.
So 1 minus an imaginary number is never going to be 0.
Right.
You're always going to have a real part.
You can't cancel out this 1.
Yep.
There's no we got to cancel out the 1 somehow. How are we gonna do it? There's no means to that end. All right. So and the denominator we can ignore because it's the numerator we want. So this part must go to 0. So sure enough, if we set 2 times the real part of s minus 1 equal to 0, add 1 to both sides, divided by 2, that's 1/2 equals real part of s. That implies real part of s equals 1/2. Therefore, whenever upsilon is equal to 0, it's going to imply real part 1/2. Does that make sense?
Yes, of course.
Because we have all of the zeros in this. All of them. So only when upsilon equals 0 will this equal 1/2. All right, now we got to move on to the type 1. We can say then real part of s equals 1/2 when upsilon equals 0 and zeta function equals 0. That's the type 1 0. Now the type 2 is a little trickier, but not by much. All right, the formatting of this kind of got a little funny. Okay, so we still have upsilon representing all of the zeros, but this time we're going to take into consideration when upsilon does not equal to 0, which if you think back to a plus b plus c equals 0, we're going to say 2 terms negate the third. Okay, that we can't reduce any further, so what we're going to do is we're going to take this upsilon and I don't have an explicit form, but right here is the explicit form in second equality, and we're going to solve for the real part of s. The way we do that is we'd expand out the s's to real part plus the I times the imaginary part, and we're going to solve for the real part, and it gives this form. And this form came from a very helpful person over at a certain university. We're not going to mention his name though. Okay. And what it gives is, we had a little different form, but it's really nice is it separates the 1/2 out of,
like Abel Plana does.
Yeah, right outside of this ugly thing. This runs into the same issue we had with the type 1, that it also never goes to 0. So if we're going to have any real part of s equals 1/2, then this second term must equal 0, but it can't.
Yeah. So let me just slow down here a little bit.
Yes.
What you're saying that 2 i's of s plus I, different kinds of I, that can never be 0. Therefore, that term can never be 0.
That whole nothing in that combination. Of
and
that
the half
term.
obviously isn't 0. So this thing on the right has got to go to, in order for that to be 0, it's got to go to minus a half.
No, we want real part. We want real part of s equal to 1/2.
Oh, right.
Yeah.
Yes. So
we
that,
want this
that
second
right
term
hand
to go to
term,
0. Yeah, the right hand
the
term
second term
cannot
has
go to
got
0.
to go to 0.
Yeah, because of the complex numbers and imaginary.
And the only way for that to happen is for upsilon of s to be 0.
Yes. So if
which means you got a contradiction.
yes, we just say there's no real part 1/2 in there. So that number
Right.
can never go to 0. So therefore, the real part of s will never equal 1/2 in the type 2 solution.
And now, in my opinion, Jeff, this is the guts of the proof right here.
The heart.
We're looking at it. So upsilon. So basically, upsilon of s not equals 0 implies upsilon of s equals 0, which is a contradiction, and therefore.
Well, yeah, we
So therefore, upsilon of s must equal 0.
We just say no. That's just not where it belongs. That's all.
Yeah.
Exactly.
Happen.
Good. So that's type 2, and then we have our 2 types now. And I think I have some of the formatting wrong, but in the paper it's right. So we're gonna ignore it because I think I grabbed these from an old giraffe. All right, lemma 4. This
should be an and, not an or, in the top of that.
Yeah, exactly. So we added this little lemma here at the end, and I like it. There were some people, that it apparently wasn't very clear that upsilon of rho equal to minus upsilon of 1 minus complex conjugate of rho was a solution. And so we put this in to show that this implies real part of rho equals 1/2.
So in your opinion, Jeff, this wasn't even necessary, this fourth lemma.
My thought is if people are going to question it, it's necessary.
Okay.
If
But
gonna,
you think it's proven without lemma form.
I
But
think
we'll add
they
it
could have
anyway.
deduced this themselves.
Okay.
But I'm
Fair enough.
happy to, I'm happy to show why.
To show
could
it
be.
explicitly.
Yeah,
All right.
it's
I agree with
it's
you.
like kind of like you get to some point in proofs. Do I need to prove that 2 + 2 = 4? No. But when it starts to get a little more complicated and you're going to different areas, better to put the lemma in, even if it's simple.
Gotcha.
Okay. All right, so we're going to start with this infinite series. So I was talking with Denny before, and Greg, I'm going to ask you this time. Why might it be good to begin with infinite series as a definition? I'll give the answer if you guys don't. If you don't
Yeah, I mean, you do run into problems. Generally, again, this is my layman's understanding. Infinite series are, I mean, you got convergence problems, you got all those kinds of issues, but you're also you're dealing with integers, whereas with functions you're dealing with analytics. So, for example, we know that the Riemann zeta is, Riemann of S is 1 over 1 to the S plus 1 over 2 to the S plus 1 over 3 to the S. Sorry, I'm writing it out here. And that's only going to give us finite numbers. We're not getting all the numbers in between, is what I'm trying to get at.
So all right,
and so that's why I feel like sometimes with the series we're not getting the robustness that we get with.
Your guys' answer is interesting because it's the exact opposite of what
I just said was completely wrong.
No, what this is why you've read Derbyshire's book Prime Obsession.
I read that about 3 years ago,
and he talks about why it's good to start with an infinite series. Is because it's impossible to disprove. So if you have a little function 1 over 2 to the power of s, and then 1 plus 1 to the power of 3 to the power of s, and you start doing this, if you keep repeating that process, it's going to go on to infinity.
Mm-hmm.
So therefore, that's a good starting point, and that is the way Euler starts with his, converting the Euler function to the product form. So, and Riemann himself, in his paper, he starts with the infinite series and ends up with the functional equation.
That could be. I'm just wondering, just in terms of information, is there more information in the integral form? Or in other words, can you derive if you have the integral form to start with, can you derive the infinite series? Or if you have the infinite series, can you derive the integral form? Can you go both ways?
My understanding is if you're going to define a function, if you have an integral form or an infinite series, both are really good for beginning the definition.
Okay. All right.
And the same reason is because you're with an integral, you're adding up little pieces too. You're kind of saying if we take this function and add it together, at this interval and this and kind of going on, you do contain all of the information if you assume an infinite that we're taking this to infinity. So with an integral, we're taking it to very infinite approximation as we zoom in on the sample to some. But an infinite series does the same thing. Long and short is if we can plug S in, then we're going to, and we get an output, we have a very strong definition. So if you a functional equation is a very poor way to define a function.
Right. Functional equation is not reversible. In other words, you can't get the infinite series or the integral from the functional equation. You can get the functional equation from either of those two.
Yeah, or at least who knows.
So information-wise, it's not as robust.
Yeah. So we start a definition. The best way to start a definition, as I have read, is start with just an infinite series. But I don't think there's anything wrong with starting an integral as well.
I'm just curious, and this is maybe a little bit off the beaten track, but now sometimes we talk about infinite products, like the Euler product.
Those are good too. Yeah. Mm-hmm.
And those are also the 3 equivalent ways.
Yes.
All have the same amount. Given any one of those 3, you can derive the other 2.
Well,
always.
Even if you don't want to, there's some you can't even derive, but they're very good starting points to define. Say we want this function to be equal to this, and Riemann he started his. He said, let's define this infinite series as zeta of S everywhere where it's finite. And
I guess where I was getting at was like the gamma function is described in terms of factorial, and you know, you have 1 factorial, 2 factorial, 3 factorial. But there isn't. It's just sort of hard to even talk about 2.6 factorial, although we can do that easily with the gamma function. That's what I was getting at, the in-betweens.
Well, the gamma function, the gamma function also has
In
an
that
infinite
case,
series
but
definition, though.
I guess in this case, we're okay. We don't run into that issue. Where there's just energy.
In general, infinite series, a good way to start a definition of a function is from an infinite series or integral or a product, infinite product. And the reason, well, we can look at that up, argue that, but it is done in most proofs. Euler's, Riemann's, it's a good starting point. So with that, we're going to define this function, and doesn't that look very similar to upsilon when at the zeta 0? Yes. So that's why we're kind of doing it. So we're starting with some different naming here, saying that we're not even zeta, and then we get this form. And sure enough, when we get g of s, and it does equal to the upsilon under these conditions. I think one of these is wrong right there. I got a typo there. Yeah, it's and, but maybe not. All right. Then when we get this, we can consider the left argument and the right. So g of s to the power of L, or the solution to the left of the critical line, is defined as g of s. Then any argument right of the critical line, but within the critical step, and substituted in, and we get that the right is equal to that. That only happens when, well, it implies, real part of SL is defined as minus 1 to the power, 1 minus R of, sorry, I don't have my glasses, I apologize.
S to the R.
SR, yeah, so it's the right-hand side. All right, such that their imaginary parts are equal. Okay, remember we were talking about the symmetry.
Yep.
All right.
Symmetry across the critical line.
If you do this, you throw this in and expand it out and substitute that in, what does it say? It says that g of s to the left is equal to minus g of s to the left.
Which means g of s to the left is 0.
Yeah, this would only happen for real part equal to half. Yes, because of the uniqueness of zero theorem. It can only be that. While upsilon of rho equals 0 for what condition? Think of the last proof. Upsilon equals 0 and zeta equals 0 means what?
Means r equals a half.
Yeah, a real part of s equals 1/2. That's what it is.
Another way of saying the same thing.
Yes. So if we're ever going to have that condition where upsilon equals minus upsilon, let's see, upsilon of rho equal to minus upsilon of 1 minus conjugate rho, that always reduces to upsilon of rho, which it can only be 0. And if it's 0, then real part 1/2. So it's just a way to kind of cut out all of that question. It's a little bit maybe unnecessary, but like I said, depends on how people think of it. Okay, so then that leaves us to the proof of the Riemann hypothesis.
So in your mind, Jeff, is that lemma 4 like a second proof? Or
it's just another lemma.
Just an additional step.
Yeah. So if somebody were to say, like, if I were just to state, everything has to be clear, right? If I were to state, somebody comes, and some people have in the comments said, no, upsilon of rho equal to minus upsilon of 1 minus complex conjugate is a solution in the type 2. They've done that. They've said that. That's a solution.
Sure. Yeah.
And I'm like, well, no, that implies real part equal 1/2.
Okay.
And then they go, well, I don't see that. It's not clear to me. Well, the reason is if you could take this in explicit form, and we start it from the infinite series, and we look at it in explicit form, you see that it reduces to that condition where it means that upsilon of rho equals 0. It can only be 0 due to the uniqueness of zero theorem. And when upsilon of rho equals 0, that automatically implies real part of rho equal 1/2. So it's not clear to people, it's not exactly clear that this solution implies real part 1/2. So we could just say, because rho equals this equals 1/2 implies 1/2, we can move forward. But like I said, a lot of people are getting stuck in there and go, no, I don't see that, and you gotta understand they're very suspicious of these proofs in the first place. So better to spell it out. Okay. Now, proof of the Riemann hypothesis falls very easily from that. All we need to do is take the two explicit forms of the type 2
And
solutions.
again, all these H's are supposed to be subscripts, not superscripts.
Yeah, in
right?
the paper they are, but I apologize.
Okay.
It's,
Okay.
So, but yeah, they just mean they're hypothetical non-trivial zeros off the critical line. All row H. All right. Good. So all we needed to do is take the type 2 solution, which remember that 1/2 plus this factor that can never go to 0, and we add two of them up with, instead of row, we have 1 minus complex conjugate row. We add those two together, and as Denny was talking in the beginning, those two real parts must equal 1. So this is the real part of one of the non-trivial zeros, hypothetical. This is the other, they must equal 1. That's the explicit form. And as you remember, this includes how many zeros? All of the zeros. Okay, so there's nothing hidden here. This is the definition.
Including the trivial zeros. Yeah.
Well, it doesn't include the ones that have real part 1/2, but it includes all zeros that don't have a real part 1/2. Can't have real part 1/2. Why? Because upsilon is 0. We already proved that they're mutually exclusive, but even if it was, upsilon would in the denominator be undefined. Anyway, this is this general solution for all zeros that don't have real part 1/2. So yes, the trivial zeros are in here, and any hypothetical zeros off the critical line are in here. We take two of them, their real parts must equal 1 if they're in the critical strip. Does that make sense?
Mm-hmm.
Okay. Well, let's break that down. What that equation simplifies, where we get 0, we can express it in this way as well. And now we have a really neat thing we can evaluate the factors. Can this first factor equal 0? No, it's the same one from lemma 3. Mm-hmm. So therefore the second factor must equal 0. And what do we get? Everything reduces to upsilon of row H equal to minus upsilon of 1 minus complex conjugate of row H, which implies what, Greg?
That the real part is 1/2.
Yes, real part is 1/2. This right here implies upsilon equals 0. This result from lemma 4.
Gotcha. Yeah.
All right. And if upsilon, so if we take the explicit form, this is basically saying, if you look at the what's that?
I failed. No. Upsilon is 0. Okay.
No, Greg.
Yes, I do.
All right,
you're showing me this, and I'm remembering it as we go. Because
it's been a while. It's been a while.
It's been a long time. So I don't. It seems like
All right, I'm gonna switch over to Denny. I'm gonna embarrass him now. Denny, what does this imply? Upsilon of row H equal to minus upsilon of 1 minus complex conjugate of row H from lemma 4.
I'm not sure. Yeah.
I'll forget. Good.
I've lost the track.
Oh no! It implies this number right here. What's that? What's that number?
0.
It means upsilon equals 0. And what's this over here? That implies what?
Row equal. It's on the critical line. Yeah.
Very good. So can we have critical zeros in the type 2 solution?
Nope.
Nope, because they're mutually exclusive. We proved that in lemma 3. Let's go back and check. Let's see. Lemma 3, right here. Can we have real part? The wrong way to look at it. Let me go back to here. Right here. So if upsilon equals 0, it means real part 1/2. This is type 2. Can we have real part of 1/2 in type 2?
No, it doesn't exist.
We can't.
Upsilon has to equal 0.
It must. So if it's not in type 1 and it's not in type 2, and we are talking about all of the zeros or some of the zeros? All of the zeros, and it's not in type 1 and it's not in type 3. Where is it? Where are the non-trivial zeros off the critical strip?
There aren't any.
There aren't any. There can't be
the
any.
whole point.
They're not in type 1 solution. They can't because they don't have real part 1/2. They can't be in type 2 because they don't sum. The real parts don't sum to 1, because that implies that upsilon equals 0. So if they're not in type 1 solution, they're not in type 2 solution, and we are talking about all of the zeros of the zeta function, are they hidden? That's why I kind of talk about the oval. Are they kind of like off screen somewhere? No, they can't exist. They can't. they're not in the type 1, type 2 solution. All the zeros must be in one or the other. So the condition is required. Now let's read this here. The condition is required because the two terms in the second factor only vanish when upsilon of rho and rho h and upsilon of 1 minus complex conjugate of rho h are equal in magnitude and have opposite signs. However, this condition was proven to imply real part 1/2 in lemma 4. Since all real part 1/2 arguments are prohibited by lemma 3 from being also in the type 2 set, the set of solutions given by type 2 is empty. The following is the only logical conclusion to the set of type 2 zeros being empty. The negative solution for the type 2 solution is extraneous. You remember it was a quadratic. While the type 2 planar solution of property 2 exists, as proven in lemma 3, it is not critically symmetric, and therefore does not comply with property 1. Can there be asymmetric non-trivial zeros off the critical line in the critical strip? No, not according to the very, very earliest finding of Riemann. And does that rely on the functional equation? It does not. The functional equation relies on that. So it's not the other way, which came first. All right. So because the type
I would
2,
let me just throw in just 2 cents again.
Well, let me finish the sentence and then we'll go.
Go ahead.
Okay.
Sorry.
So because the type 2 solution describes all the zeros of the Riemann zeta function that do not have a real part 1/2, as proven in lemma 3, the type 2 solution contains only trivial zeros. Because all non-trivial zeros must comply with the symmetric vertices property, no non-trivial zeros could exist as type 2 solutions. And because there are only 2 types of solution for all the zeros of zeta function, all the non-trivial zeros of the Riemann zeta function are restricted to the type 1 solution. Since the type 1 solution is on the critical line, all the non-trivial zeros of the Riemann zeta function have real part 1/2. And the Riemann hypothesis is correct. Yes, Greg.
Well, I just got to try to summarize the whole thing. First of all, because this problem has been around for 170 years, 160 years.
Yeah.
It's assumed that the solution is really complicated and is going to involve a lot of highfalutin math and all that kind of stuff. But the reality of this solution is that the guts of it is really all about just a couple of simple pieces of logic applied to this Riemann oscillator, and that was Jeff's genius, was to see that we can write the Riemann function however we want. We can just define some function upsilon of s and then write it in whatever form we want. It turned out to be valuable to write it in this particular form, which is this oscillator form. And you could play all kinds of games, which believe me, I've done. Reversing the upsilon and treating that as a forcing function with the zeta sub s function. You can do all kinds of interesting things. But my point is that that was all done arbitrarily. He chose to make that form, and then he just discovered some things about the upsilon function and what that would mean in terms of the Riemann hypothesis. So it's kind of seemed almost the actual solution is so simple. It's like it's almost easy to miss. But there's a couple of logical steps that you need to go through, and that's the hard part, is getting past all these logical steps. But once you get past, the math is really not that complicated, and that's what's so mind blowing about this solution, is that it's really not. But you have to. I don't see a way to do it other than to use this oscillator that has been generated for the paper, and Jeff gets all the credit for that.
Well,
anyway,
yeah.
So that's my 2 cents.
I appreciate it. But let me say, it's kind of like an invention. If you're creating a light bulb, you're inventing a light bulb, and you've never done it before. You have to try it in many different configurations and see which one works and what turns it on. This fit. I've tried many other configurations too. It didn't fit. So this is the solution. That's why. I mean, finding that is that is the hard part. It's like only Edison, got the right components at the right time to turn the light bulb on. But heating up an element and lighting up is not hard. But getting it just the right configuration so that everything lines up and there's no contradictions, that's we can say that the Riemann hypothesis or the Riemann zeta function is like an oscillator. It naturally is there. Now, I mean, It's it works. I've done a lot of graphs with it, and I like the oscillator itself. Even when t is not equal to 0, it's kind of you can make some really neat shapes with it. I've done that.
I've played with that too.
Yeah, so I think I got a comment in the video. Somebody else has wanted to do it too. So yeah, because it's you can do a lot of things. You could take the spiral and wrap it around cone, a sphere, and all sorts of neat things, and it's really kind of neat. So
my guess is that it will be connected to some other things, and then maybe that's a good segue to your announcement, Jeff. I don't want to.
Yes, it's a very big announcement. I got two. One I think is one is better for other people. One is better for us. Let's deal with the one that's better for us.
Jeff, can I ask a question?
Yes, go for the question. Yeah.
You published, you completed over 100-page proof of this Riemann hypothesis. Is this what we're seeing now, just what that boils down to?
This was not 100 pages. This is about 10, 15 pages.
Well, the original one was close to that.
The original one, yeah.
One so that you wrote 4 years ago.
Okay. All right. So there was one. No, you're gonna go back further. That was a long time ago. That was like 10,
I remember
15
that one,
years ago. Yeah, that was a while. Okay. So that one. What I found in that. What I found was that I didn't know that the zeta function formed an oscillator. I just know it could be thought of as a thermodynamic system. And so the other proof did work, but I did find an error in it, and it could have been easily avoided. You know what I mean? It's like it's kind of one of the steps. Has an error, but it still could be.
I would just like to say, my contribution to this, really the proof is all Jeff's, but my contribution in a way was trying to help simplify it, take it from that 100-page thing down to what it is today, which is much shorter, and getting it to the essence.
I don't think you can give yourself enough justice. You have it's incredible. I mean, the hours that we spent of getting me trying to explain it, and getting you to understand, even to see. I mean, it was
getting me to understand anything takes a long time.
No, I know we were going. It was like there was some heated conversations. And then Denny too at the beginning, I said over, he's like, no, can't get past equation 1. This is wrong. And I'm like going, what? And he would go put it in.
Denny's the math guy.
And then I go and I'm like,
when it comes to math.
Like, this is wrong. And I'm like, what? And so there was a lot of refinement. So I had an unrefined idea. Let's just put it that way. And you guys helped polish it up into a nice neat package.
So let's hear about your new unrefined idea.
Well, you remember a couple of years ago, 5 years ago, when I first brought up the Riemann hypothesis, I said this is closely related to another proof. Yep. And that is the Birch-Swinnerton-Dyer conjecture. So,
9 reads we're up to. Wow.
Yeah, but no one's even able to read it at all. It's private.
Okay.
So you guys have your stuff to finish editing before I release it. You know what I mean?
We're gonna do that.
Yes, and this is a direct proof for the Birch-Swinnerton-Dyer conjecture.
And same process. I'll just say Jeff wrote it, but Denny and I have sort of put a lot of feedback into it, and that's what we're doing. With this one as well.
So what I would have first presented, no one would have accepted. So there's really Greg's like, no, let's see what the analytic continuation of K function looks like, and that, and so, and then there was some analysis that Denny really was able to work out, and we had to confirm. But together.
But I'll say this: the guts of the proof haven't really changed. Just same thing as with the first paper. Your intuition was spot on from the beginning, but it's taken a long time to get it to the point where it's presentable to a larger group. So, anyway.
Yes, and I think it's very nice and neat. Like I said, we'll kind of go through it for a couple more weeks, but we did find the answer to the big questions. This was not in the original draft, but Greg's suggestions has led this to become a possibility that we are able to find the value of the L function of an elliptic curve at s equals 1 for rank equals 0, which was what Birch and Swinnerton-Dyer themselves said was too difficult to do in order to prove the conjecture. So we do have that value. Everything this is minus 1 over 2c. This is a constant and does not equal 0, and we do have it defined. plus 1 plus the Euler-Mascheroni constant plus log of 4. That is the values. So C is ends up being a constant that comes from the number of solutions on the elliptic curve and rational solutions. And it does, when you take that function and you take the Taylor expansion, it does equal what the conjecture predicts.
All three of these equations are number 65. I just want to point that out.
Yeah, that's a typo. We have
I know how that
some work
goes.
to do. But they're yeah. So we so that proof. I mean, it doesn't even involve multiple lemmas. It's just it goes straight through equation. Do this. Almost all is algebraic manipulations and analysis. There's no complex conjugates in this, so we don't need to run. So there's a lot of complex analysis in this. Not a lot, but there's a couple points where they're critical points. So we have the paper, the proof is done, but you see there's little things like the numbering of the equations and that we're gonna format it. But the next video, I'm gonna present it in a way that was done with the other one, the other Birch and Swinner, with the Riemann hypothesis proof. But just to be clear, this is a very good proof. I am even more confident of this one at first draft than the other. It's a very solid proof. You don't need to worry about all all the zeros hiding off somewhere. It's really straightforward. The means to, well, we're going to get into another video of how things were discovered. Not even going to discuss it. But there is another solution, another announcement. And I'm starting a podcast, and this is where I would like to highlight other people's work. And not only with mathematics, but with science, technology, health, human, development, and a range of things. I am getting together my guest lists right now. Some people that I really want to have on it. But what I need everyone to do is I'm going to show the intro, the teaser is in the comments below in this video. Is going to be a link to the channel, and please please subscribe. Some of the guests that I have that I know are going to want to wait to come on to the show when we have more subscribers. But
chicken and egg.
Yeah, so we need people to come over and just start subscribing.
You can get me early.
Good. I'll get some people because
I don't know
everyone's
how much
gonna watch
them.
Because when I see a new channel, I go back and I watch them all the way to the beginning. Once I kind of exhaust and what do they call that? What do they call that when they're binge watching? Yeah. So I'll binge watch all their videos, and then I go back to the beginning. I'm like, at the beginning, I watched them all, and there's none out yet. So I watch when I really like a channel. I will watch all of them. I'll go way back to the beginning. This was something that I started years ago, but was planning, got the website, but wasn't going to do it until the Birch and Swinner Dyer conjecture was released. So because I didn't want to get distracted, I figure that is enough. I can move on, and I really want to highlight other people's work because, like some of the things you were talking, Greg, was one guy who translated the Ampere's laws to English and things. These guys are still alive, right? Or no?
Well, he's at my age, yeah.
Yeah, so
he's in Brazil.
So
he's an awesome guy. He would be great to have.
Yeah, and there's like I said, a handful of people that I know and I've corresponded with before. I'd really like to get them on, and it's not just math because this is not going to be interesting to everyone. It's really, I'm going to show you the teaser, and let's play. Ready? It's not a teaser. It's just the intro. But we on our end and heard everything. So you guys
Okay, I
interrupted.
didn't hear any
Now we hear
music,
your
but I
voices.
have seen the video. It's great. Really, really.
Okay, so
really
this
nice.
is just so the set is being built as we speak. It's gonna be really nice, and obviously got to work out the technical issues, and then I got to start getting the guests. I think I got a good handful that I'd like to have on, but researchers, if you would like, one, go comment, go subscribe, and you can. The only video is up there right now, and it's gonna be there for a few weeks. So we're gonna start this in January. Go and you can start putting comments in that video that you just watched there. That's just that 30-second snippet of guests that you would like to see on. Make sure they're alive, and I will start to kind of see if there's this common theme of what people want. This is going to be a podcast for you, the viewers. It is not going to be my own research. It's going to be for other people's research that I want to highlight. And again, it's not only mathematics. It's nobody else's show, so we can do anything we want with it. But I do like the idea of alternative science and alternative concepts, and I'm also really
There's not a lot of that out there, Jeff. I mean, there's a lot of people in this world like Denny and me and you who are just kind of off on our own doing research. And, you haven't talked a lot about our understandings of physics, but we'd spend most of our time actually in that realm. And there are thousands of us throughout the world. I mean, it may be approaching 10,000 people who are independent, who have views that are outside the mainstream. That we've been told to believe certain things in having to do with Einsteinian physics, having to do with cold fusion, having to do with energy. What constitutes energy and what's quack science and what's not. And believe me, there's plenty of people who have really great credentials who are thought of, I guess, as pseudoscience, or just generally not even, just ignored. People have no idea that they even exist.
I want to use those who maybe don't have good credentials. You remember Neil Adams?
Neil Adams is one. Yeah, he's been into Expanding Earth.
He's a character too. I love his work.
Exactly.
And
he did the Batman cartoons.
Yeah, the Batman cartoons. But
that's his credential.
Very significant findings. And I love it when people argue it because he starts cursing. It's so awesome. Do you remember that conference?
I remember Neil. Sure.
But there's others.
I just want to point out there's lots of people like that.
Yes.
And most of those people, most of them are completely unknown. They're working on their own, and they don't have a platform or a voice or anything. But they're out there. I guarantee it. I know a lot of them.
Well, this is the one guest I want right now. I want Perlman.
Perlman?
Yeah. Oh, you don't know him?
Yeah, I want him. Well, I want to get Birch.
It's
not John Birch.
John Birch is still alive. Yeah.
It's not John, is it? It can't be John. Is it John Birch?
Brian Birch.
Anyway. Brian Birch.
Birch,
I don't know his name, but anyway, he's still alive, and we need to get him on. That'd be awesome.
Yes, but I want Perlman. He solved one of the millennial problems.
Gregory Perlman, yeah.
So why
the only person to solve any of the millennial problems so far in mathematics?
Accepted.
Correct.
Yeah. So I would like.
We saw two of them, but they're not accepted yet.
Yes. So please, if anyone is over in Russia, knows him, knows somewhere how to get in contact with him,
does he speak English? I mean, that is kind of important. But
there's translation
services. Yeah, we can work around.
My wife, her Russian's not that good.
Probably doesn't know a lot of Russian.
We will find. Even if maybe he has a friend there who could translate. Look, we'd like to talk with you. That's the thing. He's the one of all the mathematicians and researchers in the world. He is the one that I would like to speak with the most. And I know a lot of people that that I want to speak with. I mean, this is really, I know you wanted it. Grigory, as I say, Grigory or Gregory. We'll just say Gregory.
I'd say Grigory, but that's Russian. Yeah.
Listen, Grigory, we want to speak with you. We're not going to put you in a spot. We know you don't like to talk with a lot of people, but I can tell you, all of us. We don't like the way the establishment mathematics community is itself we see
We're
as very
not part of that.
problematic, and we just want to. Actually, I don't even want to talk. I just want to bring you on and have you talk and just tell us a little bit so people can get to know you a little bit. If you don't want, that's okay. Maybe an email, something would be great. But that would be my ideal for this. Anyway, this will be starting in a few weeks. Everyone, please go subscribe to that channel. Link will be in the bottom of this. Denny, Greg, and thank you. Anything else last
Well,
minute?
we're a little bit over the half an hour you originally said, unless you edit the heck out of this thing.
I'll try to edit as much as I can. But all right,
but it was fun.
That's okay.
Thank you, Jeff.
So if we have the goal a half hour, it turns into 2 hours. It still ends sometime.
That's typical.
Well, you know what I'm doing with the podcast is I'm getting an hourglass. And I'm going to put it on the table, and it'll kind of keep me at time. But it's one that angles, so I can slow it down. If I like conversation, I can slow the speed. So I'm getting that because I don't have any clock here, and I never keep time. I can sit there and talk for hours. All right, but that'll be good. Good. I will talk to you soon. So I will be putting up a couple more videos on the Birchett-Swinnerton-Dyer conjecture. The Riemann hypothesis, I'm sorry, is proven. Please, if you do find an error, I would be very interested. And also very surprised. We have 21,000 reads. I highly doubt that non-mathematicians are going and looking this up. Okay, these are
12,000 reads, right?
What's that?
12,000 reads.
12,000. Sorry, 12,000 plus reads, and these are mathematicians. We have sent it. I made a list of mathematicians who I've sent it to and correspond with some of them. I mean, top mathematicians. There are no errors found. There are none. Okay, and I know because they've even admitted so. Will they go on record and life, a career on the line to defend it? They haven't yet, but
somebody will.
It's inevitable. It's inevitable. It has to. And if not, then Birchett-Swinnerton-Dyer conjecture, and then we'll just do another one and another one.
Keep plugging away. Well, I don't know. There aren't any others in the can that I know of, but
yeah, there are the P equals NP problem.
Oh.
That one
That's a big one.
I'm fully convinced that it is P does not equal NP, but that's all about time complexity.
In other words, there's no free lunch.
No,
I mean, right? All the programs that in terms of like keeping your data safe and all that stuff and all the mathematical stuff is based on that very thing.
Well, that's why I'm interested in it, because the Riemann hypothesis, if it were false, it would say that the original encryption is not as good as we thought it was. And the same with the Birchett-Swinnerton-Dyer conjecture. If it was false, then it's not as then elliptic curve cryptography is not as.
And by the way, it's true. Just that's a bit of a spoiler, but yeah.
Yeah, so we found that it's correct. So the security is as good as expected, and the P equals NP. Well, I don't know. I'd rather not go there because I've worked on it. It's very hard. All of them are hard. I'd rather not. I'd rather be focusing my time on other people's research. But obviously, if it's a matter of acceptance, then I will continue to work on proofs to find one that is acceptable, because the proofs are straightforward, as you saw. I mean, it doesn't get much more straightforward than a direct proof, and there's no gray area, there's no errors. I mean, Denny and Greg are very top-notch mathematicians. In fact, Greg, I am going to do that podcast with you with your little Rain Man trick with the quadratic equation. I got lots of stuff. Very, very good mathematicians. I'm not saying we're better mathematicians than anyone in the world at all. No, but not poor mathematicians either. So, and like I said, we have sent this all over, not everywhere, but waiting for Perlman. Contact us. Okay, we got to end, or it's never end. Guys, have a good evening. Thank you.
You too.
Talk to you later.
Thanks, Jeff. Thanks, Denny.
Thanks,
Bye.
Jeff. Thanks, Greg.